Okay, I apologize for the low tech. I cannot get my bamboo tablet to work. So rather than having kindergarten handwriting, we're just gonna see my hand in the video. So sorry about that. So section 6.1 is talking about composite functions. So function composition, which is an operation. So the operation is read f of g of x. These two notations both mean the same thing. This is composite notation, this is nested notation, and they both mean f of g of x. They're both function composition. It's just another operation, just like adding functions, dividing functions, etc. So we've got three different main types of problems that you're going to need to be able to understand and do. First one is when you're given certain functions and you're asked to find composite functions that involve inputs that are numbers. So this reads f of g of x. This is, again, equivalent to the nested notation that would look like this, f of g of 5 in this case. And so when we have this type of function, we work from the inside out. So my first step is going to be to find g of 5. So f of, and now I'm going to find g of 5. So that means plug in 5 in this rule in place of x. So square root of, instead of x, my input is 5, so 5 plus 4. And then I'm going to simplify. So 5 plus 4 is obviously 9, and the square root of 9 is 3. So this simplifies to f of 3. So now we've created it back into an Algebra 1 problem. Function notation, f of 3, means plug in 3 to the f function. So f of 3 means I'm going to do 3 squared minus 5 times 3. So I plug 3 in everywhere. 3 squared is 9. 5 times 3 is 15. And so 9 minus 15 gives us our final answer of -6. So f of g of 5 is -6. And when I have a number input, I should get a number output. Part B, g of f of 0. So I'm not going to rewrite the nested notation this time. Whatever comes second, that's the inside function. G is the outside function in this case. So g of f of 0. So f of 0 is the inside, and it means I'm going to plug 0 in here. So 0 squared minus 5 times 0. So 0 squared is 0, 5 times 0 is 0. So this simplifies to g of 0, which means put 0 in here. So square root of 0 plus 4, which square root of 4 is 2. Okay, hopefully you're getting the hang of this. This last one is really just here to make sure you understand that we are allowed to compose a function with itself. So the inside function and the outside function have the same rule. That does not actually change what we're doing. So I find g of 0 first, and then I'm going to find g of that result. Now, normally I would write that all out, but I already did work for g of 0 over here. So there's no reason for me to write square root of 0 plus 4 again when I've already showed the work and I've shown that g of 0 is 2. So I did this part. G of 0 is 2. So now I have g of 2. And so that means plug in 2 in place of x in the g of x function. 2 plus 4 is 6, so I've got square root of 6, which is not divisible by any perfect square factors, so we can't simplify that radical, and that is in simplest form. Okay, so that's type 1. where you're finding a function composition using actual numbers. Type 2 is when we're finding function compositions, so same idea, f of g, g of f of f, but we're doing so with no input given. When no input is given, the input is understood to be x. So meaning we're just dealing with the actual equation and function rules themselves. So A, f of g means f of, and then I plug in the rule for the function named g, which is x plus 4 over 2x minus 5. So this notation, again, goes back to Algebra 1. And if I had a highlighter, I would highlight this, but instead I'll just use a different color here. When I have f of this, anything, it doesn't matter what you put in the parentheses. You could put a polynomial that has like 8 terms in here if you want. But the meaning of it is that I am going to take out the variable everywhere it appears in the function named f, and in its place, I'm going to put in this whole thing. So everything else about the function stays the same. I still have the 2, I still have the minus 1. But in place of the x, I'm going to put this whole thing, x plus 4 over 2x minus 5. And then I do the same thing in the denominator because it also has an x. So in place of that x, I put in this whole thing, x plus 4 over 2x minus 5, and then I followed that up with a minus 2. So now I need to simplify. Numerator first, 2 times this fraction. Remember, it's 2 over 1, so top times top, bottom times bottom. So 2x plus 8 over 1 times anything is just itself. Then I have minus 1. I know that I'm going to have to simplify this numerator, and you can't add and subtract fractions without a common denominator. So I know my common denominator needs to be 2x minus 5. So if I multiply the denominator of 1 over 1 times 2x minus 5, I do the same to the numerator. So instead of 1, I have this fraction. The denominator, same idea. I need to have a common denominator, but this time, because it's 2, that's like 2 over 1. So I multiply 1 times 2x minus 5. Now I need to multiply 2 times 2x minus 5. So 2 times 2x minus 5 is 4x minus 10. So we're reviewing simple middle school rules of fractions here, but in the context of polynomials. When I have two fractions that already have the same denominator, and I'm adding or subtracting, the denominator doesn't change, so 1/3 plus 1/3 is 2/3. The denominator stays the same, I just deal with the numerator. And in this case, my numerator are polynomials. So I have 2x minus 2x, which is 0. Then I have 8 minus negative 5, which is positive 13. I do the same thing in the denominator. They've already got the same common denominator. So I do x minus 4x, which is negative 3x. 4 minus negative 10 is positive 14. So I realize that now you would think you might be done, but we're not done. We have simplified the numerator as far as it'll go. We did the same with the denominator. But remember that fraction bars are the division operation. This is saying to do 13 over 2x minus 5 and divide it by this fraction. Remember that dividing fractions, we really multiply by the reciprocal. So that's what I'm doing here. I can cross-reduce these because they're the exact same factors. And so I end up with 13 over negative 3x plus 14. Notice in the directions that it says state the domain of each. Now, we talked about this when we did the other function operations. So when we did adding, subtracting, multiplying, dividing. It is not just the final answer where we have to consider the domain. We have to consider, in this case, anything that would ever give a 0 in the denominator or a negative under a square root in any of the steps. So in my first couple steps, I've got a denominator of 2x minus 5 in a lot of places. So I know that 2x minus 5 can't be 0 because if it is, my denominator is 0, which I know is not possible. So add 5 to both sides, divide by 2. That means that x can't be 5/2. As I work through my work, I don't see any different denominators until I get here. Now I also know that negative 3x plus 14 can't be 0. So subtract 14 on both sides, divide by negative 3. X can't be 14/3 either. So it says, find the composition, state the domain of each. If it doesn't specify the form, then you can choose. In this case, we're most familiar with intervals, so I'll do interval notation in this case. I can go from negative infinity up to and including, or not including, sorry, not equal to, 5/2. Then from 5/2 to 14/3, and then from 14/3 to infinity. So this is our answer. Okay, tried to straighten it, went the wrong way. Okay. Part B, I'm going to do in a different color, and I'm going to kind of take it down this way. We're only going to need a little bit of space for example 3. So we'll look at part B over here. It wants us to find g of f. So g of 2x minus 1 over x minus 2. So I'm going to plug this whole fraction into the g of x function. So x now becomes that whole fraction. This is my new input. So input plus 4 over 2 times the input minus 5. And then this works pretty much the same as A, but I wanted to go through it at least twice. So in the top, this is 4 over 1. If I multiply the bottom by x minus 2, I also have to multiply the top by 4x, or by x minus 2. So my first fraction is 2x minus 1 over x minus 2. My second fraction, when I get it the common denominator, is 4x minus 8. In the denominator, multiply by 2. In the first fraction, sorry, I should have moved that up. So 2 over 1, so top times top, bottom times bottom. 4x minus 2 over x minus 2. And then the minus 5. Again, I need it to have the same denominator. So if I multiply the bottom times x minus 2, I have to do the same on the top. So minus 5 times x, 5 times negative 2. 1 times x minus 2 is x minus 2. Next step, they have a common denominator, so simplify the numerators. 2x plus 4x is 6x. Negative 1 plus negative 8 is negative 9. And that's over x minus 2. I'm going to be dividing that by this result. So I know this is the denominator. I have 4x minus 5x, which is negative x. Negative 2 minus negative 10, which is negative 2 plus 10, which is 8. Like we talked about in the last example, dividing fractions is the same as multiplying by the reciprocal. So in this case, I can cross-reduce those two. And my numerator is 6x minus 9. My denominator is negative x plus 8. Technically, we should factor that top because it's not in simplest form. However, sometimes in the back of the book they don't, mainly because nothing cancels by factoring. If it did cancel, you wouldn't have a choice, but here nothing cancels. So domain restrictions, I know that negative x plus 8 can't be 0. So subtract 8, and x can't be 8. I also know that x minus 2 can't be 0, because all of these are x minus 2's in the denominator. So that means x can't be 2. So here's my result. My domain, if I were to write, let's say, set notation form, x such that x is not equal to 2 and 8. And again, you don't have to use set notation. If you prefer to always use interval, that's fine. Or if you like inequality, it doesn't matter as long as the directions didn't specify. All right, we're going to go ahead and skip f of f because we've already illustrated by example C here that you can compose a function with itself. The other thing that I do want to point out is notice that the answer to part A for f of g, which is right here, is not the same as the answer for part B, which is g of f. So the order of the composition matters. It's not going to be the same. If you switch what's the inside function, you're usually not going to get the same answer. Okay, last one. Find functions f and g so that f of g equals h. So on this one, h of x is equivalent to f of g of x. And what it wants us to do is just find functions f and g that when I compose them in this order, it would simplify to this guy. So this is almost like, it's not quite as bad, but I think of it as kind of like when you have to teach proofs, that you're trying to teach someone how to think, and it's the same idea here. The main strategy that I can say is that you're trying to identify an outside and an inside rule. And once you do that, you can figure out what the functions are. So in this case, f is the outside function, and kind of on the outside of this function, I have a cube root. So because of that, I'm going to say that f of x is the cube root of x. That's the outside. I've got a cube root of something. The inside is what I have the cube root of, x squared minus 9. So the inside function should equal that. And you can always check your work. If you do f of g of x, that means f of cube root of x squared minus 9, which is exactly what I'm looking for. There are some occasions where there might be more than one correct answer, for this type of problem. Again, yours doesn't always have to be the same as someone else's to be correct. So make sure you just double check your thinking before you finalize your answer. All right. Hopefully that helps and refreshes your memory from what you may or may not already know about composite functions. And so make sure you refer to your practice homework list to know which problems you need to do.